And we have, once again, we have front page 81. Okay, we have for problem number 57. And here we have an equation. Okay, so we have in the variable u, okay, so you have 4u squared plus 64 is equal to 0. And again, you can either factor out the 4, or you could just ultimately divide the equation by 4 in the later steps. And so we have a single variable term in 4u squared, and we're looking at solving for u. And if I start out by isolating 4u squared, okay, so I have 4u squared is equal to negative 64. And if I write, okay, the left-hand side of the equation in terms of u squared, so we're going to have with division by 4, okay, so we had that u squared is equal to negative 16. Okay, and again, reverting to the square root property of equality. So if I go from u squared to u, like just as I go from x squared to x, and then we had that which represents p, I'm going to go over to the plus and minus square root of p, where we have p to be at negative 16, and 16 is a perfect square value, and the square root of 16 is 4. But in the case of negative 16, its square root, okay, is going to be 4i. So we have for the roots, okay, that define the solutions to the equation. Again, we have both to be complex. Okay, so we have 4i as well as minus 4i. Okay, and for what we have in the case of the next item, and we have with number 58, okay, here we have the equation in terms of the variable p, and for what we have in this one, okay, same sort of dynamic in the follow through. Okay, so we have here we have 8p squared plus 72 is equal to 0. So we have just a single variable term that is squared, and again, I have a coefficient I can either factor out and just solve by factoring and setting, like if I factored out 8, I'll have times quantity of p squared plus 9 is equal to 0. So I can solve through factoring and then using the square root property of equality, or I can just go ahead and isolate the p squared term without doing division or factoring out right away. And so we have, by subtracting 72, so we have 8p squared is equal to negative 72, and upon dividing both sides by 8, okay, so you have p squared is equal to negative 9, and as I go from p squared to p, so I have plus or minus, okay, the square root of negative 9, and here we will once again have additive inverse complex terms, okay, and we have plus or minus, and the square root of negative 9, we have plus or minus 3i. So we have in the results, we have 3i and negative 3i. And we have just in the case of the next item, and here we have a quadratic equation in the variable t, and for what we have in number 61, okay, we got t squared minus 8t is equal to negative 24. Okay, and Okay, so now the first two exercises had just a single variable term. Now we have two, and this is a quadratic equation. And if I take what I have here and rewrite in terms of standard form, okay, we're going to have, in this case, a trinomial. Okay, that will be set equal to 0. So here we're going to have t squared minus 8t plus 24 is equal to 0. And okay, now I cannot factor what I have into real integer coefficients. If I think of like 1 times 24, product is at 24, and there are no integer factors of 24 that will add up to negative 8. You might have combinations like negative 24, negative 1, sum is negative 25. Negative 12 and 2, sum is negative 10, and or I should say negative 12 and negative 2. So the sum be negative 14, negative 6, and negative 4. Sum is at negative 10. And there's no combination that will add up to negative 8. Okay, so we have as a recourse, okay, we can use the quadratic formula. So we have from t squared, okay, we have that a is equal to 1. And from negative 8t, okay, we have that b is equal to negative 8. And we have plus 24 at the end. Okay, we have that c is equal to 24. And just taking what we have in the setup. Okay, now we're solving for t and not x, but everything else is going to be a duplication of the process, but we are still looking at negative b plus or minus, okay, the square root of b squared minus 4ac all over 2a, and for the opposite sign of b, okay, so you have subtraction of negative 8. You have plus or minus, okay, the square root. And for b squared, okay, so you have the square of negative 8. And for 4ac, we have minus 4 times 1 times 24. And we have all over 2a, okay, so with a at 1, okay, we have 2 times 1. Okay, now looking at what we have inside the radical. Okay, now the square of negative 8 is going to be a positive 64. And we have minus, okay, we have 4 times 1. Minus 4 times 1 is negative 4. Negative 4 times 24 is negative 96. And 64 minus 96 is equal to negative 32. Okay. Now for the square root of negative 32, okay, we can just initiate just going ahead and drawing out the letter I. Okay, and we have with the square root of 32, I. Now for the square root of 32, again, we do not have a perfect square, but 32 is a multiple of perfect squares greater than 1, and the highest value is going to be at 16. And so just looking at what we have now, so we have the square root of 16 times the square root of 2 times I. Okay, so we have 4 times, okay, the square root of 2i. And for what we have in following through, okay, so we have 8 plus or minus. We have 4 times the square root of 2i. And 2 times 1 is 2, and we have even valued coefficients, and you can either factor out 2 from the numerator and denominator, or you could just write separately. We have 8 halves plus or minus, okay, 4 times the square root of 2i all over 2. And so we have 8 halves is going to be 4. And we have plus or minus, and 2 into 4 times the square root of 2i. Okay, so this will be 2 times the square root of 2i. Okay. All right. And so, and you can write either in compact form And again, you can separate as 4 plus 2 times the square root of 2i. And 4 minus 2 times the square root of 2i. Okay, so far, okay, we have in our equations, okay, we have once again complex roots and another setting, and here we have with number 68. And we have for this one, okay, so you have what's going to be a quadratic equation in the variable m. Right now we have m times, okay, the quantity of m plus 10 is equal to minus 34. And just taking care, and again, you will not use the zero product property with the setup. Again, you can only set the factors and solve from the factor form if the equation is set equal to 0. But we have instead the number negative 34 on the right. So what we have to do here is just remove the parentheses. So we have with the distributing, we have m all over the quantity of m plus 10. So you have m squared plus 10m is equal to negative 34. And then looking at, once again, expressing this quadratic equation in standard form. Okay, so we have with our trinomial, okay, so we're going to have m squared plus 10m plus 34, okay, is equal to 0. Okay, and here we have another trinomial that we cannot factor into real integer coefficients. Okay, so again, just reverting to the quadratic formula. Okay, so we have a is equal to 1. And we have that b is equal to 10. And also we have that c is equal to 34. And so we have, once again, using the quadratic formula. Okay, so you have with negative b, so we have negative 10 plus or minus. Okay, we have the square root. Again, so we have b squared will be 10 squared. We have minus 4 ac, so you have minus 4 times 1 times 34. And we have all over 2a, okay, which is going to be 2 times 1. And so just looking at what we have now, okay, we have inside the radical. Okay, so you have 10 squared is going to be 100. Negative 4 times 1 is negative 4. Negative 4 times 34 is going to be a negative 136. Okay, so you have a negative difference. And for the square root of negative 36, okay, you just go ahead and write out the result. So again, you have 36 is a perfect square number. So the square root of negative 36, okay, is going to be 6i. Or the square root of negative 36 is going to be 6i. Okay, and so just transporting what we have from the radicals. So we have negative 10 plus or minus, okay, 6i. And we have all over 2. Okay. And you can either factor out 2 halves, 2 from the numerator, 2 from the denominator, or just in compact form. So we have negative 10 plus or minus 6i all over 2. So you have like negative 10 halves, which would be negative 5. You got plus or minus 6i over 2, and that's going to be plus or minus 3i. Again, we have with separating, so we have negative 5 plus 3i, as well as negative 5 minus 3i. Okay, so we still have maintaining the trend of where, okay, we have complex roots in the solutions. Okay, now, and for what we have in the case of 71, I think we'll have this trend to continue. Okay, and here, okay, we have 9x squared plus 49, okay, is equal to 0. And if I isolate the variable term, so it's kind of like the very first two problems, we have a single variable term, okay, where the variable is squared. And just like what I did, I think it was like 4u squared and 8p squared from earlier, I'm going to isolate 9x squared, okay, by subtracting the constant, or taking out the constant that was alongside it. And so we're going to have in the rewrite, okay, so we're going to have 9x squared so 9x squared is equal to negative 49, okay, and we have with division by 9. Okay, so you have the x squared is equal to negative 49 ninths. And we have with the square root property of equality, so going from x squared to x. So we have x equal to plus or minus the square root of negative 49 ninths. And just taking this out just a little bit further. Okay, so you have plus or minus the square root of 49 ninths I. And if you notice, both 49 and 9 are perfect square values. So we have for the square root of negative 49 ninths, okay, we have for x, we have plus or minus 7/3 of I. And again, just separating, so we have 7/3 of I, as well as minus 7/3 of I. Okay, now, again, I had mentioned that there will be equations that can potentially have a blend of real and complex roots. And now, for one particular family of such equations, now we're going to have what will be referred to as equations that are quadratic in form. Okay, and they won't, in the purest sense, they will not be quadratic equations, but just but you still want to have if you have two variable terms, you're going to have like a 2-to-1 ratio in terms of comparing the greater degree to the smaller degree in the letter. And now, for equations that are quadratic in form, okay, we have equations again, in purest sense, okay, not quadratic equations. you can say that we have equations where if there are two terms in the dependent variable, then the higher order term is going to be twice the degree of the lower order term. And I'll just place emphasis on this in case you have twice the degree. Okay, and we'll just say that we have among the examples, not to solve, but just kind of put on display. If I have, let's say, x to the fourth plus 19x squared plus 1 is equal to 0, and if you notice, okay, for the degrees, okay, so we have like a 4:2 ratio. And for this equation, okay, that one is going to be said to be quadratic in x squared. Now let's say if I have, as another instance, if I have something like 3x squared let me change that order. So you have 3x to the 6th minus 4x cubed minus 17 is equal to 0. Okay. And if you notice, okay, we have for the higher and lower order degrees in x, okay, so you have like a 6:3 ratio. So you have 6:3 is 2, and this equation will be said to be quadratic in the lower order variable and degrees. So this equation will be quadratic in x cubed. And let's say if I have little change up here. If I have, let's say, negative 5x I have plus 7 times, okay, the square root of x minus 6 is equal to 0. Okay. And again, if I were to give this explicitly in degree terms, so I have like negative 5x. Now for 7 times, okay, the square root of x, remember, we have implicitly that the index number of a square root is going to be the number 2. And inside the second root we have x to the first. So rewriting the square root of x in degree terms, so I'm going to have x to the 1/2. So you have negative 5x plus 7 times x to the 1/2 minus 6 is equal to 0. So the higher degree we have at 1. Lower degree we have at 1/2. This one, so you have 1 divided by 1/2. So this will translate to 1 times the reciprocal of the denominator. So you still have a 2-to-1 ratio between 1 and 1/2. And this equation will be said to exist as an equation that is quadratic in the square root of x or x to the 1/2. Okay, so you have, these are just samples of equations that are quadratic in form, where you have, like, again, 2 variable expressions where the higher order expression is twice the degree of the lower order expression. And let's say that if you're looking at equations that are quadratic in form, and that we are looking at solving for x. Okay. And just a bit of a sampler here. Okay, see if I have x to the 4th plus 3x squared minus 4 is equal to 0. So if I have x to the 4th plus 3x squared minus 4 is equal to 0, now this equation is going to be quadratic in x squared. And whatever the equation is quadratic in, and I can factor, I'm going to factor in terms of the expression that the equation is quadratic in. So we have quadratic in x squared. And you don't have to identify what the equation is quadratic in, but just kind of provide a bit of signaling in terms of how the follow-through is going to arise. So that times itself, like x times x will go into x squared. And for x to the 4th, that which will multiply itself into x to the 4th, okay, that is going to be x to the 2nd. And here we have with factors of -4, whose sum or difference will be at 3. So we're going to have more weight given to the addition than to the subtraction. So we have x squared plus 4. And we have times the quantity of what is going to be x squared minus 1. Okay. And once again, okay, now you have your options in terms of how to go about x squared minus 1. Now, a difference to squares such as x squared minus 1, okay, you can factor, but now for x squared plus 4, we cannot. So I'm just going to take this one step further. For x squared minus 1, okay, we can factor this as x plus 1 and x minus 1. And looking at setting each of the factors to 0. Okay, so for x squared plus 4 equal to 0. Okay, so if I take 4 away from both sides, so you have x squared equal to -4. And if I go from x squared to x, so we have x equal to plus or minus the square root of -4. So again, so we have square root of 4 is 2, but that of -4 is going to be 2i. So for x squared equal to -4, we have 2 complex solutions where x is equal to positive and negative 2i. And if x plus 1 is equal to 0, I'm going to take away 1. For x minus 1 equal to 0, I would add 1 to both sides. So for x plus 1 equal to 0, so we're going to have the x is equal to -1. For x minus 1 equal to 0, I have the x is equal to 1. So I'm going to have 4 solutions in the mix. Okay, and we'll have two complex solutions with 2i and negative 2i, and also two real valued solutions with negative and positive 1. Okay, and not always the case necessarily, but just for what we had here. So we had a fourth order equations. Say if the equation is a conditional, okay, which this is. So you have a fourth order equation, so you have possibly 4 solutions. Not necessarily that many right away, because you might have like a squared trinomial where you would not have 4 solutions, but there is the possibility. So the degree of the equation signals that you might have that many solutions, and we did. We had 2 real solutions and 2 complex solutions. And let's say that if you have, for another case, all right, if I have, let's say, x to the 4th minus 81 is equal to 0. Okay. And, okay, so I have x to the 4th all over again. And, okay, if you notice, now this equation is going to be quadratic in x squared, okay, but we have only one variable term with x to the 4th. And, okay, and I can still factor x to the 4th as x squared times itself. Okay, so for what we have here, so for negative 81, I can factor to x squared plus 9 and x squared minus 9. And I'm just going to mention again, we have a sum of squares now. Again, this is not factorable. And technically for x squared minus 9, this being a difference of squares, okay, this one is factorable. So I could expand this to x plus and x minus 3. But what I'm going to do here, okay, so I have the quantity of x squared plus 9 times x squared minus 9 is equal to 0. Now I could factor x squared minus 9, but say if you did not want to factor and you decided to go ahead and use, okay, the square root property of equality in both of these. So I can go ahead and set the equations to 0. So you have x squared plus 9 is equal to 0, and x squared minus 9 is equal to 0, and setting x squared where it's going to be by itself on the left hand side, so I can take 9 away from both sides in the first. For x squared minus 9, okay, so I can add 9 to both sides, so I'm going to have that x squared is equal to negative 9, and if I go ahead and apply the square root property of equality, so x squared will go to x is equal to plus or minus, okay, the square root of negative 9. And so for what we will have here, x is going to be plus or minus 3i. And as for x squared minus 9 is equal to 0, okay, so we have the x squared is equal to 9. And if we go from x squared to x, you have plus or minus the square root of 9. Okay, and so we're going to have here that x is equal to plus or minus 3. So we have 4 solutions, okay, where we have a mixed bag of real and complex solutions. So we're going to have, like for the complex values, we have negative and positive 3i. And for what we have among, okay, the real values here, okay, so we're going to have positive as well as -3. And tell you what, just for the next few moments, okay, in terms of, say, solving for x, okay, among equations that are quadratic in form, and we'll say that we have and we'll leave these in fourth order right now, but we'll get to other degrees as well. And we'll say that we have x to the fourth plus 6x squared minus 16 is equal to 0. And we'll say that we have x to the fourth minus 256 is equal to 0. Okay, so for the next few moments, okay, let's see what values of x we get between these two equations. Okay, tell you what, if we go ahead and look into the first equation, so here we have x to the fourth plus 6x squared minus 16 is equal to 0. And again, this equation we have to be quadratic in x squared. And if I factor x to the fourth, so we're going to have x squared and x squared. And for what we will have here, okay, so factors of -16 whose sum or difference will be on the plus side at 6. Okay, so you have, let's say we have x squared plus 8. We have times the quantity of x squared minus 2 is equal to 0. Okay, and for what we have in the layout, okay, so we have x squared plus 8 and x squared minus 2. And if I set the factors equal to 0, so if I have x squared plus 8 equal to 0, okay, again, I can isolate x squared upon subtracting 8 on both sides. So we're going to have that x squared is equal to -8. And we have in the follow through, okay, so we have with the square root property of equality. Okay, so going from x squared to x. So I have x at plus or minus, okay, the square root of -8. And we have plus or minus the square root of 8 times I. And again, just sort of rephrase here. Okay, so we have the square root of 8. We have the square root of 4 times the square root of 2. And for the square root of 8, okay, that is reducible to 2 times, okay, the square root of 2. So we have for the solutions in x from the first factor, okay, we have plus or minus 2 times the square root of 2 times I, or 2i times the square root of 2. Now for x squared minus 2, okay, now you could technically, in a way, factor x squared minus 2 to like x plus and x minus the square root of 2. Okay, but now in terms of integers, 2 is not a perfect square number. And if I add 2 to both sides, so we have the x squared is equal to 2. And utilizing the square root property of equality, okay, so we have the x is equal to plus or minus, okay, the square root of 2. do here. All right, so you have plus or minus 2 times the square root of 2i, as well as plus or minus the square root of 2. And again, this equation had possibly up to 4 solutions, and it does. And we have with those solutions, whereupon we have 2 coming from the complex domain, where we have plus or minus 2 times the square root of 2i. And I'll itemize these. Okay, so you have 2 times the square root of 2i. Then we have the negative of 2 times, okay, the square root of 2i, and then for the rest, we have the square root of 2, as well as the negative of the square root of 2. All right, now for x to the fourth minus 256, okay, for these, okay, we have a difference of squares. Okay, for x to the fourth is going to be the square of x squared once again. And for negative 256, now 256 is a perfect square number, where this would factor to x squared plus and x squared minus 16. Now we'll mention, okay, when I work with, say, x squared plus 9 and x squared minus 9, I decided to use the square root property of equality for both sets of factors, but I could have factored x squared minus 9. And I could apply the same brand of treatment for this problem. But what I want to do here is that with x squared minus 16, I'll just go ahead and factor this one out. So x squared minus 16, okay, we can have this to factor to x plus and x minus 4. And so we have setting each of the factors to 0. Okay, so you have x squared plus 16 is equal to 0, and then upon isolating x squared, so you have x squared is equal to negative 16. And so go from x squared to x, so I have plus or minus, okay, the square root of negative 16. And 16 is a perfect square number, and the negative of that is going to have its square root to go to 4i. So for x, we have plus or minus 4i. And as for x plus 4, and x minus 4 equal to 0. Okay, so I have, so from x plus 4, I have x equal to negative 4. And from x minus 4 equal to 0, I have that x is equal to 4. Okay, and so we have another quartet of solutions, 2 that are complex with positive and negative 4i. And again, 2 real values with negative and positive 4. And we have from the set of problems, okay, originating from page 81, and for the equations that are quadratic in form, let's see, and that was, okay, and the first of those, okay, we have with number 92. Okay, now for this one, okay, we are kind of breaking out to an equation quadratic in form, where we have the equation to be of an entirely different degree. And we have for this one, okay, so for 92, okay, so we have what's going to be in the variable d, so you have 3 times d to the 2/3, okay, and you have minus d to the 1/3. And we have minus 4 is equal to 0. Now this particular equation, notice we have a 2-to-1 ratio between 2/3 and 1/3. Okay, and so we would have this equation to be quadratic in d to the 1/3 and I'm going to factor this particular trinomial, or I should say this particular expression in the form of d to the 1/3. And let me give you just sort of a parallel here. If I had like 3x squared minus x minus 4 is equal to 0. Now your 3x squared would factor out to 3x and x. So 3x times x would be 3x squared, and looking for the right combination of factors in -4 such that the outside and the inside products would add up to negative x. Okay, now -4 could factor out to +2, -2, -2 +2, +4 -1, or -4 +1, but the -4 +1 checks out. 3x times x is 3x squared. We got plus 3x minus 4x goes to -1x, and then we have -4. And just so for what I have here, instead of x squared and x, I'm going to have d to the 2/3 and d to the 1/3. So just applying the same brand of treatment. So you have like x goes to d to the 1/3. So for 3d to the 2/3, this will factor out to 3d to the 1/3. Then we have -4. Times the quantity. This is going to be d to the 1/3 plus 1 is equal to 0. So you have the same proportions among the degrees and coefficients. Now, looking at using the zero product property. So for the first equation, okay, so you have 3d to the 1/3 minus 4 is equal to 0. And if I isolate the d term, so we have it adding 4 to both sides. So we have 3d to the 1/3 is equal to 4. And if I divide by 3, so we have d to the 1/3 is equal to 4/3. Okay, so we're back in the terrain, once again, of working with equations that do not have integer exponents. Okay, so you have d to the 1/3 is equal to 4/3. And if I go from non-integer exponent to radical, again, d to the 1/3, okay, that is going to be the cubic root of d is equal to 4/3. And then getting rid of the radical, so I'm going to take both sides and raise to the 3rd power . And so we have for one set of solutions, okay, cubic root of d to the 3rd goes to d. 4 cubed is 64. 3 cubed is 27. So one solution in d is going to be 64/27. Now for the other factor, okay, so you have d to the 1/3 plus 1 is equal to 0, and isolating d to the 1/3 upon subtracting. Okay, so I'm going to have d to the 1/3 is equal to -1. And so rewriting d to the 1/3 in radical terms, okay, so I have the cubic root of d is equal to -1, and then we have upon cubing both sides, okay, Cubic root of d cubed goes to d. Negative 1 to the third, you have negative 1 times itself, so this will go to negative 1. So when we have with the positive fraction 20, yeah, so they have 27 to 64. Okay, so they have d at 64/27. And the other solution we have with negative 1. And now another case, right? And we have with number 94. Okay, so another change up in the degrees. And here we have n to the 1/2. And we have plus 6n to the 1/4. You have minus 16 is equal to 0. Now we have, in the variable n, we have a couple of terms, one with the degree of 1/2, the other with the degree of 1/4, and 1/2 is twice the degree of what we have in the 1/4 power. Okay, so this equation, okay, this will be quadratic in n to the 1/4. And again, just operating on a parallel. Okay, so you have like a 2-to-1 ratio, kind of like x squared plus 6x minus 16 is equal to 0. And again, you have with your factors, you would have, again, so you would have x plus 8 and x minus 2. But instead of x squared and x, I'm having n to the 1/2 and n to the 1/4. And so just taking the factors, maintaining the proportions as well as the coefficients. So say like n to the 1/2 is to x squared as n to the 1/4 is to x. So for x plus 8, we're going to have n to the 1/4 plus 8. And we have times quantity of n to the 1/4 minus 2. Again, we have equal to 0. So we have from the setup, okay, we have in the variable factors, okay, so I have n to the 1/4 plus 8 and n to the 1/4 minus 2. And if I set each of these equal to 0, okay, so we have for the first, so I have n to the 1/4 is equal to negative 8. And then for the other, I have n to the 1/4 is equal to positive 2. And if I translate both of these statements in terms of radicals, so we have the 4th root of n is equal to negative 8. And for the other, I have the 4th root of n is equal to 2. And if you notice, we have even root radicals. And again, we have the principal square root rule, okay, again, which states that, okay, the even roots of an expression cannot reduce to a negative constant. Well, guess what? We have with the 4th root of n and trying to set this equal to negative 8, that particular part, and it's because of the negative sign, there's going to be no solution. Again, principal square root rule applies only to even roots, but it doesn't apply to like cubic roots or fifth roots. Now for the other, we have the 4th root of n is equal to 2. And I can proceed since we have a positive 2. And if I take care of this radical upon raising both sides to the fourth power, say the fourth root of n to the fourth, okay, so the roots and the exponent cancel each other out, and we'll free up n, and for 2 to the fourth, okay, that is going to go to 16. So there's going to be only one solution for n, and that is going to be with the number 16. All right. And we will be looking into other cases regarding equations quadratic in form. But for what we have right now, for inequalities, kind of going back, okay, we'll be looking at inequalities and take those in the realm of working with absolute value. And just to give you a sample of statements, if I have something like an inequality such as, let's do a little bit of color coding here. If I have that x is greater than 2, and I represent this on a number line, and I think I'll copy this. Okay, so for x is greater than 2, okay, what you might have here is like an Alex notation. If you were to take a graph for x is greater than 2, then we have what will be an open circle on 2, and then we have, in terms of the direction of the inequality, well, this is going to be a ray that will go out continuously to the right. And there's going to be a notation where we have for the interval solution, if you notice, okay, we have x is greater than 2, and to represent this symbolically in interval notation, okay, so have going past 2, and since 2 is not included, you're going to have a parenthesis to go around this, and the arrow head going continuously to the right. This means that you have constantly increasing and approaching infinity. So this would be the interval solution or display of what we have to represent x is greater than 2. And let's say that if I have another situation, I have that x is greater than or equal to -1. Okay, so for x is greater than or equal to -1. Okay, so the equal sign signals that -1 is going to be included, and on the graph we're going to have a closed point. And for the greater than or equal sign, okay, so equal, okay, that's your points. Greater than portion, again, you're going to have a ray that will go out to the right. And for the interval solution, so we have going from and including -1. So this time, to represent the inclusion of -1, you're going to have a bracket. And again, we have increasing continuously on out to infinity. I don't know why things are so jumpy today, but anyway. So yeah, going from including -1 on out to infinity. And we have, let's say in the next case, say if I change course and say that I have that x is less than 0. So for x is less than 0, okay, so 0 is not included. So you're going to have a hole or an open circle on 0. And for less than 0, this time I'm going to have a ray that will go in the other direction. And for the interval notation on this one, and reading in order from left to right, okay, so we have, now before we had continuous increase, where we have approaching infinity, but now for a continuous decrease, we have the lower limit approaching -infinity, and the upper limit you have approaching but not quite including 0, so the 0 is going to be also in the parenthesis. And let's say that for an inequality statement, say if we had the x is less than or equal to 2, okay, so for x is less than or equal to 2, and again, the equal sign signals that 2 is included. And from this, okay, the rest will be less than, so I'm going to have a ray that's going to go out to the left. And for the interval display, now the lower limit, okay, we have right at -infinity, and the upper limit, okay, we have going up to and including 2, and that value is going to be bracketed. And let's say that if I have all real numbers, okay, so for all real numbers, okay, so what this is going to mean is that you will have continuity throughout at both ends. And for the interval notation, that which will represent the set of all real numbers, we have tying in the extremes, okay, so you have going from -infinity heading on out to the upper end, which is approaching positive infinity, okay. And the reason I have, okay, the infinities, okay, to be in parentheses, so think of it kind of like an expanding universe. Okay, so we have, in this case, there we go. Okay, think of it like an expanding universe, so infinities keep stretching on out, thus the use of the parentheses. And let's say that if you have, for a compound inequality statement, and we'll say that we have that -3 is going to be less than or equal to x, which in turn is going to be less than 2. Oops. Let me do this. Okay, so for negative 3 is less than or equal to x is less than 2. So negative 3 is alongside x, and we have the equal sign for this portion of the compound inequality included. So that means that negative 3 is going to be part of the solution. Now x is less than 2. This will signal that 2 is not included. So you're going to have a hole or a circle on 2. And then for all the values of x, okay, so you have negative 3 included, and then you have those other values, okay, that will be greater than 3, however, less than 2. So you have a line segment here. And for what you're going to have in the case of the interval notation, okay, so you have between negative 3 and 2. This time you have no infinities involved. You don't have going continuously to the right or to the left, just this containment. And negative 3 is included, so this will be in the bracket. And 2 is not included, so that is going to stay in the parentheses. So you're kind of looking at like going from negative 3 up to like 1.999999, but never getting exactly to 2. And let me mention some things here. Just kind of come out with a little bit of a composite regarding absolute value inequalities and equations. Okay. Okay, so for what we have regarding absolute value, again, if k is a non-negative value, and okay, I'm just going back to the equation. So if k is non-negative, and we have that the absolute value of x is equal to k, then you have that x is equal to plus or minus k so you have k as well as negative k. Now, where the inequalities come in, okay, if we have it that the absolute value of x is less than k, then you're going to have that negative k is less than x is less than k. And so for your interval notation, okay, so this would be like in parentheses you have negative to positive k. And if we have that the absolute value of x is less than or equal to k, then you're going to have that negative k is less than or equal to x is less than or equal to k. And just the interval notation, you have negative k to k, and you have the containment of these k terms in the brackets. Now, where you have sort of going in polar opposite directions, if we have, let's say that we've got that the absolute value of x is greater than k, then we have two distinct inequality stages. Okay, we have at the one end, if the absolute value of x is greater than k, once you take out the absolute value notation, we have that either x is going to be increasingly negative, or that x is going to be increasingly positive. And one might ask, okay, how would you put this in interval notation terms? Well, for x is less than negative k, you have like going from negative infinity approaching negative k. And for the other extreme, we have going past k and have on out to infinity. Okay, and for this symbol here, U is going to refer to union of intervals or sets. And we have, finally, okay, in the case of the absolute value of x is greater than or equal to k, we have almost the exact same statement as before, but with the equal signs included for both sections. So you have x is less than or equal to negative k, or that x is greater than or equal to k. And just the interval notation translation. So you have negative infinity to negative k in the bracket. And the other portion you have k, since k is included, that is going to be bracketed, and we have going on out to infinity. All right, and we will be looking into some of the applications regarding what we have with the inequalities, and especially as we cross over into the absolute value applications. Again, the class activity 1 set, okay, that'll be due Saturday, January the 30th at 11:59 p.m. And the Alex Homeworks sections R6 and R8. I don't know why my equipment just keeps acting up. Sorry about that. Okay, so I have section R6 is due Monday, February the 1st, and section R8 is due Wednesday, February the 3rd at 11:59 p.m. And again, I do have the video simulations for those items up in the weekly notes tab. And then we have from pages 102 to 103, go ahead and be looking at numbers 9, 10, 16, 27, 28, 48, and also number 58.